Tonight, Comet R21 passes close to Earth and is visible without a telescope. Two ancient cosmic travelers, dormant for millennia in the most remote regions of our solar system, have begun their majestic awakening. It is October 2025, and these messengers from the cosmos are approaching our small blue planet with a grace that defies human imagination. Vladimir Basugli, an amateur Ukrainian astronomer, could never have imagined that his nightly dedication to examining images from the SWAN instrument aboard the Soho Solar Observatory would forever change our understanding of this, the 9th of October 2025. While most of the world slept, his experienced eyes detected something unusual, a fuzzy spot with a tail stretching approximately 2 degrees across the stars of the Virgo constellation. He had discovered what would later be known as Comet C divided by 2025 R2, or redos, more familiarly called SWAN. But this would not be the only gift the cosmos would offer us. During these weeks of October, almost simultaneously, another ancient traveler discovered, months earlier, by the Mount Lemmon telescope in Arizona, and cataloged as C divided by 2025, a sixth Lemmon was also approaching its closest point to Earth. Two comets, two cosmic stories, separated by hundreds of thousands of years in their orbits, converging in our night sky to create a spectacle no living generation had witnessed. Hello and welcome to our journey through the celestial visitors of October 2025. Tonight, we explore the extraordinary cosmic encounter unfolding above our heads, as two ancient comets perform their closest celestial dance to Earth in hundreds of thousands of years. Before we continue deeper into the stories of these cosmic travelers, take a moment to get comfortable, wherever you are listening, perhaps in bed during a quiet night walk, or in a peaceful moment of your day. If stories like this help you relax and discover new wonders, consider subscribing or liking this program. It helps more curious minds connect with these relaxing explorations. Now let your thoughts flow as we continue unraveling the mysteries of these ancient messengers who have crossed the cosmic void to visit us. Comets, those architects of ice and rock that dance on the edges of our solar system, carry stories that predate human civilization. When C divided by 2025 R2, Redo's SWAN, began its latest orbit into the inner solar system, mammoths still roamed the Earth, and our ancestors were just beginning to master fire. Its orbital period, calculated at approximately 22,500 years, makes it a silent witness to epochs we can barely imagine. The story of its discovery is fascinating in itself. The SWAN instrument, which stands for Solar Wind Anisotropy, was initially designed to study the solar wind, but its unique ability to detect hydrogen in space has made it an exceptional comet hunter. Vladimir Basugli, working from his home in Ukraine, is part of a global network of amateur astronomers who dedicate their nights to scrutinizing these images for unexpected visitors. His discovery of SWAN marks the 20th comet officially identified through this instrument, a feat that speaks both to his dedication and the technological marvel that makes such a discovery possible from the comfort of home. But the SWAN comet does not travel alone in its approach to Earth. During this memorable October, the Lemmon Comet, discovered by the Mount Lemmon Survey Telescope on the 3rd of January 2025, follows an equally fascinating trajectory with an original orbital period of approximately 1,350 years. This visitor has witnessed significant historical events on its last approach: the construction of the first Gothic cathedrals, the rise and fall of medieval empires, and the first exploratory voyages that connected continents. What makes this October 2025 truly exceptional is not just the presence of these two comets, but their almost perfect timing. On October 20, SWAN will reach its closest point to Earth, approaching just 0.26 astronomical units from our planet. This equals approximately 24 million miles, a distance that, while vast by earthly standards, represents an extraordinary proximity on a cosmic scale. Just one day later, on October 21, Lemmon will follow its example, approaching 0.6 astronomical units, or about 56 million miles. These distances, translated into more understandable terms, mean that both comets will be considerably closer than Mars at its closest approach to Earth. For ground observers, this presents an opportunity unprecedented to witness not one, but two cometary displays simultaneously, each visible to the naked eye, under optimal viewing conditions. The process leading to these cosmic encounters began long before any human civilization existed. Both comets originated in extremely distant regions of our solar system. Swan, according to the most recent measurements, may have emerged from the Oort cloud, that hypothetical sphere of icy objects, surrounding our solar system at distances that defy comprehension. Lemon, with its shorter but equally ancient orbit, probably formed in similarly remote regions, shaped by the same primordial gravitational forces that shaped our cosmic neighborhood. The journey of these comets toward their rendezvous with Earth has not been a straight line through space. For millennia, their orbits have been influenced by the gravitational pull of the giant planets, especially Jupiter, whose immense mass acts as a kind of cosmic conductor, subtly altering the trajectories of these distant travelers. Each approach to the inner solar system slightly modifies their future orbits, creating a gravitational ballet of mathematical precision and aesthetic beauty. The technology that made these discoveries possible represents one of the most remarkable triumphs of modern astronomy. The ATLAS telescope, part of the early warning system for Earth-impacting asteroids, uses a network of ground-based telescopes equipped with high-sensitivity CCD cameras capable of detecting objects extremely faint against the starry background. These instruments can identify brightness changes as subtle as a candle flame seen from several miles away, allowing them to detect comets while they are still far from the Sun and relatively inactive. The SWAN instrument, for its part, represents a different but equally impressive innovation, mounted aboard the Soho Solar Observatory orbiting at the Lagrange point between Earth and the Sunday. SWAN can detect the emission of neutral hydrogen surrounding comet nuclei. When comets approach the Sun, the ice on their surfaces begins to sublimate, releasing water vapor that subsequently dissociates into hydrogen and oxygen under the influence of ultraviolet solar radiation. This hydrogen emission creates an extensive cloud around the comet that SWAN can detect even when the comet itself is too faint to be seen in visible light. The data collected on these two comets have revealed fascinating features about their composition and structure. SWAN, with its visible tail extending approximately 5 degrees across the sky, equivalent to 10 full moons placed side by side, shows signs of robust cometary activity. Its nucleus, probably no larger than a few miles in diameter, is ejecting enough material to create this impressive tail that ground observers can appreciate even with modest binoculars. Lemon, although initially more modest in behavior, has shown a pattern of increasing brightness, suggesting that its nucleus is beginning to respond more vigorously to solar heating. Astronomers have observed that its ion tail, that bluish, straight structure formed by electrically charged particles, has developed complex features, including knots and spirals created by its interaction with the variable solar wind. This October 2025 marks not only an exceptional astronomical event, but also a moment of convergence between citizen science and professional research. The discoveries of Vladimir Basugli and the Mount Lemmon survey team demonstrate how modern astronomy relies as much on advanced technology as on the trained human eye and personal dedication. Thousands of amateur astronomers worldwide regularly contribute to these discoveries, dedicating their nights to the patient search for these cosmic visitors. The approach of these comets also represents an opportunity. Unprecedented educational institutions, planetariums, and astronomical societies around the world have organized special observation events, taking advantage of this unique moment to inspire a new generation of explorers. Cosmic, the relative ease with which these comets can be observed makes them perfect ambassadors for astronomy, accessible both to experienced observers and to those who lift their eyes to the night sky for the first time with scientific curiosity. As these ancient travelers continue their approach toward their closest point to Earth, they carry with them not only ice and rock, formed at the dawn of our solar system, but also the promise of connection to something much larger than our everyday experiences. In a world often dominated by immediate concerns and limited horizons, the presence of these comets reminds us of our place within a vast and dynamic cosmos where events unfold on timescales that transcend human generations. The awakening of these ancient travelers during this October of 2025 invites us to participate in a shared experience with observers from all cultures and continents under the same night sky that has inspired poets, navigators, and dreamers for millennia. We have the opportunity to witness a spectacle that connects our present moment with the vast timescales of the cosmos, reminding us that we are part of a much larger story than we can imagine. When we lift our gaze to the night sky in search of our October comet visitors, there is something that immediately captures our attention: a distinctive, soft, greenish glow that envelops the nucleus of these ancient travelers like an ethereal cloak. This phenomenon, observed in comets throughout human history, holds one of the most beautiful and scientifically fascinating secrets of the cosmos. The emerald green color that characterizes many comets is no coincidence nor an optical illusion. It is the result of an extraordinary molecular ballet unfolding in deep space, where the laws of quantum physics manifest in a spectacle visible to our earthly eyes. This greenish glow tells the story of ancient molecules awakening under the caress of solar radiation, beginning a dance that ends in their own destruction. And paradoxically, in the creation of one of the most beautiful phenomena we can behold, at the heart of this mystery lies a simple but extraordinary molecule: diatomic carbon, chemically known as C2. This molecule, formed by only 2 carbon atoms joined by one of the strongest bonds known in nature, is found abundantly in cometary nuclei, preserved in primordial ice. From the earliest days of our solar system, during the long millennia these comets have spent in the cold, dark regions of outer space. These molecules have remained dormant, frozen in a stillness that has lasted since before complex life appeared on our planet. But when our October comets began their journey toward the inner solar system, something extraordinary began to happen. As they approached the sun, intense solar radiation started to warm their icy surfaces. The ice, composed mainly of water but also containing carbon monoxide, carbon dioxide, and other complex organic compounds, began to sublimate directly from solid to gas, creating the temporary atmosphere we call the coma. Within this coma, the diatomic carbon molecules, freed from their icy prison, are suddenly exposed to the intense ultraviolet radiation of the sun. This radiation, invisible to our eyes but extraordinarily energetic, acts like a key that unlocks the quantum secrets of these carbon molecules. When ultraviolet photons strike the C2 molecules, they provide exactly the amount of energy needed to raise the carbon electrons to higher energy states. This process of electronic excitation is where the magic of the green glow truly begins. The diatomic carbon molecules, now in an energetically unstable state, cannot remain so indefinitely. Following the immutable laws of quantum physics, they must release this excess energy and return to their ground state. But the way they do it is what creates the visual spectacle that we so admire. When these excited molecules return to their lowest energy state, they release photons of light with very specific wavelengths. The particular electronic transition that occurs in diatomic carbon produces light in the green region of the electromagnetic spectrum, specifically around 517 nanometers in wavelength. This emission is technically known as the Swan bands, named after the British astronomer William Swan, who first identified them in 1856. What's fascinating about this process is its quantum precision. The specific wavelength of the emitted green light is not random, but is determined by the exact difference in energy levels between the excited and ground electronic states of diatomic carbon. This quantum precision means that every comet containing diatomic carbon will exhibit exactly the same shade of green, creating a kind of universal cosmic signature that we can recognize and study. But the story of cometary green glow doesn't end with the light emission. There's another equally fascinating aspect of this phenomenon: its transient nature. The diatomic carbon molecules that create this beautiful glow have a very short lifespan. Once released into the comet's coma, the same ultraviolet solar radiation that excites them to produce green light also gradually destroys them through a process called photodissociation. Researchers at the Australian National University and their international colleagues have demonstrated in the lab that diatomic carbon molecules in space have a half-life of approximately 2 days once exposed to intense solar radiation. This discovery explains why the green glow is mainly concentrated in the comet's coma, the region closest to the nucleus, but is noticeably absent in the longer tail that extends behind the comet. The cometary tail, that spectacular structure, which can stretch for millions of miles through space, is primarily composed of dust and ions that have been expelled from the coma by solar radiation pressure and the solar wind. By the time the particles reach the tail, the diatomic carbon molecules have already been destroyed by solar radiation, leaving only the products of their breakdown individual carbon atoms that do not exhibit the same characteristic green emission. This phenomenon creates a fascinating visual dichotomy in the appearance of comets. While the coma shines with its characteristic emerald green glow, the tail can show colors that are completely different. The dust tail, made up of tiny solid particles that reflect sunlight, typically appears yellowish or white, similar to the color of direct sunlight. The ion tail, formed by atoms and molecules that have lost or gained electrons under the influence of the solar wind, can glow blue or violet. Due to the characteristic emissions of ions like ionized carbon monoxide, the intensity of the green glow varies considerably, depending on several factors. The specific composition of the comet's nucleus plays a crucial role, since not all comets contain the same amounts of carbon compounds. Comets that originated in different regions of our primordial solar system or that formed under slightly different conditions may exhibit variations in the intensity of their green glow. The comet's distance from the Sun also dramatically affects the intensity of this phenomenon. When comets are farther from the Sun, the ultraviolet radiation is too weak to efficiently excite the diatomic carbon molecules, resulting in a very faint or absent green glow. It is only when they approach to about 3 astronomical units from the Sun, the distance between the Sun and the asteroid belt, that the green glow begins to become prominent. During the approach of our October 2025 comets, this green glow gradually intensifies as they near perihelion. Observers with binoculars can begin to detect this characteristic color. Several weeks before closest approach, when the comets are still relatively distant, as they get closer, the glow becomes more intense and more easily detectable until on the days of closest approach, it can even be visible to the naked eye under dark skies. The observation of the comet's green glow also connects us to a scientific tradition spanning over a century. The first spectroscopists working with instruments primitive by modern standards were able to identify the spectral features of diatomic carbon in comets. Long before we fully understood the underlying quantum mechanisms, their meticulous observations laid the groundwork for our modern understanding of cometary chemistry. The study of the green glow has also revealed valuable information about conditions in the primordial solar system. The diatomic carbon molecules, preserved in cometary nuclei, are relics from that ancient era, formed under conditions that no longer exist in our modern solar system. By studying these molecules and their behavior when released, scientists can infer details about the temperature, pressure, and chemical composition of the protoplanetary disk from which our solar system formed. Besides diatomic carbon, comets also contain other molecules that can contribute to the green glow, although to a lesser extent. Cyanogen, a molecule composed of carbon and nitrogen, also emits green wavelengths when excited by solar radiation. Although its contribution is typically smaller than that of diatomic carbon, it can add subtle variations to the tone and intensity of the observed green glow. Modern technology has allowed us to study this phenomenon with unprecedented detail. Spectrometers mounted on ground-based telescopes can break down cometary light into its individual spectral components, allowing astronomers to identify not only the presence of diatomic carbon, but also measure its relative abundance and study variations in its emission as the comet evolves during its solar approach. Space missions. have also greatly contributed to our understanding of this phenomenon. Probes like Rosetta, which accompanied Comet 67P, divided by Churyumov-Gerasimenko during its solar approach, provided direct measurements of the cometary coma's composition and confirmed many of our theories about the green emission mechanisms. This scientific knowledge, however, does not diminish the aesthetic wonder of the phenomenon at all. On the contrary, understanding the underlying quantum mechanisms that create the green glow adds an additional dimension of appreciation. Every time we observe that soft emerald glow enveloping a comet's nucleus, we are witnessing a process that connects the most fundamental levels of physical reality with the visual beauty accessible to our senses. As we contemplate the green glow of our October 2025 visitors, we can reflect on the fact that we are observing individual molecules undergoing quantum transitions, a phenomenon operating on scales so small it defies imagination, but manifests on a scale so vast it can be appreciated across millions of miles of space. This green glow is essentially the universe's way of turning the most abstract principles of quantum mechanics into a visual symphony we can behold and admire. From our little blue planet in the silent vastness of space, where there are no roads or signs marking the way, our October comets follow invisible but precise routes, traced by gravitational forces that have shaped their trajectories. Over hundreds of thousands of years, these ancient travelers do not move randomly through the cosmos, but dance, following a cosmic choreography of extraordinary mathematical precision, navigating celestial routes that connect the most remote regions of our solar system with the warmth of our earthly neighborhood. Imagine for a moment the timescale of these journeys. When Comet C, divided by 2025 R3, Swan completed its previous orbit roughly 22,500 years ago, the last ice age was coming to an end on Earth. Glaciers that had covered vast expanses of Europe and North America were beginning their slow retreat, and our human ancestors were developing the first techniques, sophisticated home and collection. While these momentous events unfolded on our small planet, Swan traveled silently through deep space, following its extreme elliptical orbit that took it to regions where sunlight is so faint it would be imperceptible to our eyes. The orbits of these comets are monuments to the elegance of the physical laws that govern our universe following Kepler's laws. Discovered more than 4 centuries ago, these celestial objects trace perfect ellipses, with the Sun occupying one of the foci. But these are not the modest ellipses of the planets we know. Cometary orbits are extremely elongated ellipses, so stretched that the difference between their closest and farthest points from the Sun is measured in tens or even hundreds of astronomical units. The Swan comet, during its long orbital journey, reaches an aphelion, its farthest point from the Sun, extending far beyond Neptune's orbit in those remote regions where the temperature approaches absolute zero, and solar radiation is so weak it can barely be distinguished from the light of distant stars. The comet remains in a state of cosmic hibernation, its nucleus composed mainly of water ices. Carbon monoxide and carbon dioxide mixed with dust and rocks stays completely frozen and inactive. But now, on its journey toward perihelion, its closest approach to the Sun, everything begins to change. The comet's speed, which had been very modest in the outer regions of its orbit, begins to increase dramatically under the growing influence of solar gravity. This acceleration is not gradual, but exponential, following physical principles formalized by Johannes Kepler in his second law. A comet sweeps out equal areas in equal times, meaning it must move faster when it is near the Sun, and more slowly when it is far away. During its closest approach to our planet, the Swan comet reaches speeds that defy everyday imagination, moving at approximately 180,000 miles per hour. This ancient cosmic traveler moves at a speed that is almost impossible to grasp in earthly terms. To put it in perspective, this speed means the comet could travel from Madrid to Buenos Aires in about 3 minutes, or completely circle the Earth in less than 9 minutes. This extraordinary speed is not the result of any internal propulsion system, but simply the manifestation of energy conservation. In the solar gravitational field, when the comet was in the most distant regions of its orbit, it had a huge amount of gravitational potential energy. Due to its distance from the Sun as it falls inward toward the solar system, this potential energy gradually converts into kinetic energy, the energy of motion resulting in speeds that increase dramatically as it approaches the Sun. The Lemon Comet follows a similar pattern but with orbital characteristics that reveal a different cosmic story with an orbital period of approximately 1,350 years before its modification by planetary gravitational effects. During this approach, Lemon represents a different class of traveler comet. Its less extreme orbit suggests it may have interacted with the outer giant planets in previous gravitational encounters that gradually altered its original trajectory. These gravitational encounters with planets like Jupiter and Saturn act as cosmic billiards, where the immense mass of these gas giants can significantly alter cometary orbits. A close encounter with Jupiter, for example, can dramatically shorten a comet's orbital period, turning it from a once-per-millennium visitor into a short-period comet that returns every few decades. Alternatively, the same type of encounter can completely eject a comet from the solar system, sending it on a hyperbolic trajectory into interstellar space. The trajectories these comets follow after their perihelion passage are equally fascinating. The close passage to the Sun not only accelerates them to extreme speeds, but also physically alters them in ways that affect their future orbits. The loss of mass due to ice sublimation and the ejection of dust and gas creates a very subtle but measurable reaction effect that can slightly alter the comet's orbit, a phenomenon known as non-gravitational force. These non-gravitational effects are particularly pronounced in comets that exhibit asymmetric activity, where gas and dust jets are ejected more intensely from one side of the nucleus than the other. This asymmetry creates a kind of natural propulsion that can speed up or slow down the comet in its orbit, depending on the orientation of the jets. Relative to the direction of orbital motion for Comet Swan, orbital calculations indicate that its next return will not occur for another approximately 22,500 years, although these numbers may be slightly adjusted, depending on the non-gravitational effects it experiences during its current passage through the inner solar system. When it returns, the Earth will have changed in ways we can barely imagine, and any civilization existing at that future time will be observing the same celestial object that we admire now, thus completing a cosmic cycle of almost incomprehensible duration. The orbital mechanics governing these movements may seem abstract, but have very practical consequences for Earth-based observers. The inclination of the comet's orbit relative to the ecliptic plane, the plane in which the Earth orbits the Sun, determines from which regions of our planet the comet will be best visible. An orbit with a high inclination can make a comet visible mainly from one hemisphere, while an orbit with a low inclination can allow observations from both hemispheres. Comet Swan, with its retrograde orbit, moves in the opposite direction. To most objects in the solar system, this orbital characteristic indicates probably an origin in the Oort cloud, that hypothetical sphere of icy objects surrounding our solar system. At distances up to 100,000 astronomical units, Oort cloud objects can have orbits with any inclination and direction. Reflecting the chaotic conditions of their formation in the early days of the solar system, the precision with which we can predict these cometary orbits represents one of the triumphs of modern mathematical astronomy using Newton's and Einstein's equations. Astronomers can calculate the future positions of these comets with extraordinary accuracy, allowing the planning of observations and space missions years or even decades in advance. However, this precision has limits, especially for comets exhibiting significant activity, as the non-gravitational effects introduce uncertainties that accumulate over time. Orbital calculations also allow us to reconstruct the past trajectories of these comets, revealing their cosmic history by mathematically tracing their orbits backward in time. Astronomers can determine when and where these objects last approached the Sun and how their orbits have been modified by gravitational encounters with planets over millennia. One of the most intriguing consequences of cometary orbital mechanics is the phenomenon known as orbital resonance. Some comets become trapped in gravitational resonances with giant planets, where their orbital periods maintain simple numerical relationships with planetary periods. For example, a comet might complete exactly 2 orbits in the time Jupiter completes 1, creating a stable situation that can persist for millions of years. The interaction between multiple planets can also create complex orbital effects known as gravitational chaos in these cases. Small perturbations can be amplified over time, causing cometary orbits to become unpredictable over long timescales. This phenomenon places fundamental limits on our ability to predict cometary positions in the distant future, adding a fundamental element of uncertainty to these apparently deterministic systems. Modern numerical integration programs use supercomputers to track cometary orbits over millions of years of evolution, taking into account perturbations from all major planets, and sometimes even the most massive asteroids. These calculations reveal that cometary orbits are fundamentally unstable on geological timescales, with most comets eventually being ejected from the solar system or impacting the Sun or a planet during their current approach. Both Swan and Lemon are being subtly influenced by the gravitational tides of the Earth and the Moon, although these effects are minuscule. Compared to the Sun's pull, they are measurable and contribute to the gradual evolution of their orbits. Astronomers use these measurements to constantly refine their orbital models and improve predictions of future approaches. The mathematical beauty of cometary orbital mechanics lies not only in its predictive accuracy, but also in its conceptual elegance. The same equations that describe the fall of an apple also govern the movement of these ancient cosmic travelers, demonstrating the universality of physical laws. When we contemplate the trajectories of our October comets, we are witnessing the geometry of space-time manifesting in motions that connect the most distant reaches of our solar system with our small cosmic corner. These invisible yet real celestial routes represent cosmic highways that have been operating long before life appeared on Earth and will continue functioning long after our planet has been transformed by stellar evolution. They are permanent reminders that we exist within a dynamic system of objects in perpetual motion, each following the gravitational laws that Johannes Kepler began to decipher 4 centuries ago, but that we are only now beginning to appreciate in all their complexity and cosmic beauty. There is a special magic in the act of looking up at the night sky, with the deliberate intention of connecting with the cosmos. As we prepare to observe our October 2025 comet visitors, we are not simply looking up. We are participating in an ancient tradition that connects all human cultures across time and space. Nighttime contemplation is both an art and a science, a practice requiring patience, preparation, and above all, an openness to the wonder that constantly surrounds us. Successful comet observation begins long before we step outside with binoculars in hand. It starts with an understanding of the natural rhythms governing both these cosmic visitors and our own planet. Comets, unlike planets, which maintain relatively predictable positions, move noticeably from night to night against the starry background, following paths that can take them from familiar constellations to regions of the sky rarely explored. During the first weeks of October 2025, our comets Swan and Lemon are in a particularly favorable phase for observation from Earth. Comet Swan, gradually emerging from solar proximity, where it had been difficult to observe, begins to gain height in the western sky after sunset. This period, known among astronomers as the increase in solar elongation, marks the moment when a comet becomes increasingly accessible to amateur observers. Solar elongation, the angular distance between the comet and the Sun, as seen from Earth, is a crucial concept for understanding observation opportunities. When this distance is less than 30 degrees, the comet remains too close to the solar glare to be easily observed. But as elongation increases, especially beyond 40 degrees, observation opportunities improve dramatically. For the Northern Hemisphere, optimal viewing conditions for Swan occur during the first hours after sunset, when the western sky has lost its twilight glow, but the comet still maintains enough height above the horizon. This delicate balance between sky darkness and comet altitude defines what astronomers call the optimal observation window. Observers in the Southern Hemisphere enjoy slightly different but equally favorable conditions. From latitudes like Argentina, Chile, or Australia, both comets reach higher altitudes, above the horizon during post-twilight hours, offering longer observation periods and generally more stable conditions. The choice of observation site is as important as selecting the right time. Light pollution is the artificial glow that emanates from modern cities. It can dramatically reduce the visibility of faint celestial objects like comets. The brightest nuclei of our October comets can be detectable even from urban locations, but their extended tails and the more subtle details of their structure are only fully revealed under truly dark skies. The search for the ideal dark sky inevitably takes us away from urban centers to rural locations, where natural darkness still prevails. National parks, nature reserves, and rural areas far away offer the best conditions, but even a trip 20 to 30 miles outside a city can produce dramatic improvements in viewing quality. Physical preparation for a night observing session involves considerations beyond optical equipment. Our eyes require about 20 to 30 minutes to fully develop their night sensitivity, a process called dark adaptation. During this period, specialized cells in our retina, called rods, adjust their chemical sensitivity, allowing us to detect light levels that would be completely imperceptible under normal lighting conditions. This dark adaptation is extraordinarily sensitive to interruption. A brief exposure to bright white light can instantly destroy 30 minutes of careful adaptation. For this reason, experienced observers use flashlights with red filters that provide enough illumination to consult star maps and adjust equipment without compromising night vision. The concept of averted vision represents another fundamental technique in observing faint celestial objects. The rods, the cells most sensitive to dim light, are concentrated in the peripheral regions of our retina, not in the center where we focus our direct attention. When we look slightly to the side of a faint comet instead of directly at it, we can detect details that would be invisible with direct vision. Binoculars emerge as the ideal companions for comet observation. Unlike telescopes, which significantly magnify but reduce the field of view, binoculars offer a perfect balance between light gathering and a wide field of view. A pair of 7x50 binoculars, which magnify 7 times and have 2-inch objective lenses, can reveal comet structures that are completely invisible to the naked eye. The binocular observing technique requires practice and patience. The comet may initially appear as a diffuse smudge, slightly brighter than the sky background. With sustained observation and dark adapted eyes, more details gradually emerge. The central condensation of the nucleus, the asymmetric extension of the coma, and perhaps even hints of the tail's structure. Telescopes, although not essential for basic observation of bright comets, can reveal extraordinary details for patient observers. A modest telescope with 4 to 6-inch aperture can show detailed structure in the coma, brightness variations along the tail, and sometimes even jets or streams of material emanating from the nucleus in specific directions. Comet photography, although technically more demanding than visual observation, offers unique rewards. Cameras can accumulate light during long exposures, revealing tail structures that extend far beyond what any visual observation can detect. A digital camera mounted on a stable tripod with exposures from 30 seconds to several minutes, depending on the comet's brightness, can capture stunning images that preserve the moment for posterity. Atmospheric conditions play a crucial role in observation quality. Nights with high humidity can create haze that significantly reduces visibility, while high-pressure conditions typically produce crystal-clear skies ideal for observing. Paradoxically, wind can be beneficial if it helps disperse atmospheric layers that distort vision, but excessive wind can make keeping optical instruments stable challenging. The lunar phase profoundly affects comet observing opportunities. During phases near the new moon, the absence of moonlight allows detecting the most subtle details of faint cometary structures. However, a waxing crescent moon can provide enough landscape illumination to make night navigation safer without significantly compromising the observation of relatively bright comets. Seasonal patterns also influence optimal observing strategies. In October, nights gradually lengthen in the northern hemisphere, providing increasingly extended observation windows. The cooler autumn temperatures often create more stable atmospheric conditions than the warm summer nights, although they require extra preparation to maintain comfort during prolonged observing sessions. Planning observing sessions greatly benefits from using star charts and planispheres that show predicted positions of comets against familiar constellations. These tools allow observers to anticipate where to look and how to recognize the correct region of the sky. Astronomical mobile apps can provide updated information on comet positions, but it's important to use these devices with screen settings that preserve dark adaptation. Recording observations, while not essential, greatly enriches the experience. Keeping a journal that documents observing conditions, visual descriptions of comets, and simple sketches creates a personal record that increases in value over time. These notes can reveal subtle changes in cometary appearance from night to night, changes that reflect the dynamic evolution of these objects as they respond to increasing solar heating. Group observing adds social and educational dimensions to the experience. Local astronomy clubs often organize special comet observing events, providing access to a variety of optical instruments and the collective expertise of experienced observers. These events can be especially valuable for novice observers who benefit from hands-on guidance and shared enthusiasm. Understanding the apparent movements of comets significantly enhances the observing experience. Unlike stars, which maintain fixed relative positions over human timescales, comets show perceptible movement even during individual observing sessions. A bright comet can move noticeably against the background stars over the course of a single night, and this movement becomes clearly apparent when observed over several hours. Patience emerges as perhaps the most important virtue. In comet observing, comets rarely reveal all their secrets immediately. The subtle structure of the tail, brightness variations in the coma, and the finer details of cometary morphology are gradually revealed to observers, who invest time in sustained contemplation. This patience is rewarded not only with better views, but also with a deeper connection to these extraordinary objects. When we finally locate our comets in the October sky and watch them slowly reveal themselves to our dark, adapted eyes, we experience something that connects directly with the most fundamental human experience: awe at the vastness and beauty of the cosmos. In that moment of silent contemplation, we become participants in a tradition stretching back to the earliest humans who lifted their gaze with curiosity to the modern astronomers who continue exploring the mysteries of the universe. In an age where technology permeates every aspect of our lives, it is comforting to discover that some of the most fascinating advances help us reconnect with the ancient rhythms of the cosmos. Astronomical mobile apps represent an extraordinary bridge between the modern digital world and the millennia-old practice of sky observation, offering tools that would have seemed magical to astronomers of previous generations, but that we now casually carry in our pockets. When we contemplate the extraordinary capability of our mobile devices to locate and track comets in real time, we witness a remarkable convergence of mathematical precision, global connectivity, and technological miniaturization. These small handheld computers can instantly access astronomical databases containing positions, orbits of hundreds of thousands of celestial objects, perform complex celestial mechanics, calculations, and present this information in an intuitive and visually appealing way. The Stellarium app, perhaps the best known among enthusiasts of astronomy, perfectly exemplifies this technological convergence. Originally developed as a planetarium program for desktop computers, Stellarium has evolved into a complete suite of astronomical tools. Available on multiple platforms, its mobile version transforms any smartphone into a portable observatory capable of showing the sky as it appears from any location on Earth, at any time in the past, present, or future, making Stellarium particularly valuable for comet tracking is its integration with regularly updated orbital databases when a new comet is discovered. As happened with Swan in September 2025, the orbital elements determined by professional astronomers are quickly incorporated into these databases, allowing the app to calculate and display the comet's positions. With extraordinary accuracy, the process behind this capability is fascinating in its technical complexity. The servers that maintain these applications regularly connect with the Minor Planet Center of the International Astronomical Union, NASA's Jet Propulsion Laboratory, and other globally recognized astronomical institutions. These organizations publish updated orbital elements that mathematically describe the orbits of comets and asteroids using parameters such as eccentricity, inclination, and longitude of the ascending node. The Bright Comets app represents another specialized approach for comet tracking, specifically designed to identify and locate the brightest visible comets from any location. This app uses algorithms that automatically prioritize the most promising objects for observation. Its augmented reality interface allows users to simply point their devices at the sky and see overlaid indicators showing exactly where to look for visible comets. This augmented reality technology represents a revolution in astronomical accessibility. Novice observers, who would previously have needed years of experience to efficiently navigate the night sky, can now locate specific celestial objects. In a matter of minutes, the app uses the device's built-in sensors, including GPS, accelerometer, digital compass, and camera, to precisely determine exactly where the user is pointing and overlay relevant astronomical information in real time. The databases that feed these apps, especially NASA's Jet Propulsion Laboratory Horizon system, represent decades of meticulous observation and mathematical calculation. Horizons can generate ephemerides, tables, showing the predicted positions of any solar system object with accuracies often reaching fractions of an arcsecond. This precision is crucial for comet tracking, as these objects can move noticeably against the star background. Even during a single night of observation, the Comet Tracker app takes a more visual and interactive approach. Its 3D simulation of the solar system allows users to explore comet orbits from perspectives impossible from Earth, visualizing how these objects move through three-dimensional space rather than simply seeing them projected against the two-dimensional sky. This perspective can provide valuable insights into why certain comets are visible from Earth at specific times, and how their orbits alternately bring them near and far from our planet. The integration of these apps with local weather services adds another practical dimension. Many astronomical apps now include weather information that helps observers plan optimal viewing sessions. The combination of cloud cover forecasts, humidity, and atmospheric transparency with information on comet positions and brightness allows for observational planning, more efficient than ever before. Push notifications represent another valuable feature of these modern applications. When a comet reaches optimal viewing conditions, it experiences a sudden increase in brightness or approaches other interesting celestial objects. The applications can automatically alert users, ensuring they don't miss significant observational events. This functionality is particularly valuable for comets like Swan and Lemon, whose brightness can fluctuate unpredictably as they approach the sun. The offline functionality of many of these applications addresses an important practical concern for observers who travel to remote locations in search of dark skies. Once the necessary data has been downloaded, applications like Stellarium can operate completely offline, providing reliable astronomical guidance even in the most remote locations. This capability is especially important for observation expeditions to national parks, deserts, or rural locations where cellular connectivity may be limited or non-existent. The built-in social sharing features in these applications have created global communities of comet observers. Users can share photographs, observation reports, and coordinates of successful locations, creating a collaborative network that enriches the experience for all participants. These social features have democratized the sharing of astronomical information, allowing exceptional discoveries and observations to spread quickly throughout the global observational community. Customization is another important aspect of modern astronomical applications. Users can configure their apps to display only the objects that interest them, adjust magnitude limit levels based on their local observing conditions, and personalize interfaces to match their preferences and experience level. This customization makes the applications equally useful for amateur astronomers, experienced and casual, occasional observers. The integration with specialized astronomical hardware represents the cutting edge of progress in applications. Many apps can now connect directly with computerized telescope mounts, CCD cameras, and other instruments, allowing full remote control of sophisticated observing equipment directly from mobile devices. This integration transforms smartphones into command centers for full amateur observatories. The timing, accuracy of these applications is particularly important for rapidly changing astronomical events, comets, especially those in highly elliptical orbits. Like our October visitors can show significant changes in brightness, position, and appearance over relatively short periods. Frequently updated apps with new orbital calculations can provide more accurate predictions than those relying on older data. The ability of these apps to simulate different observing conditions is extraordinarily valuable for planning. Users can explore how comets will appear from different latitudes under varying light pollution conditions and at different times throughout the night. This functionality allows observers to optimize their observing strategies without costly trial and error. Time outdoors applications have also made astronomical education more accessible than ever. Many include extensive databases of educational information about celestial objects, explanations of astronomical phenomena, and interactive tutorials that help users develop observing skills. This educational feature turns every observing session into a structured learning opportunity. The inherent portability of mobile apps makes them ideal companions for astronomical trips. Observers can carry entire libraries of astronomical information to remote locations without the weight and inconvenience of multiple reference books, star atlases, and ephemeris tables. This portability has made observational astronomy more accessible for travelers and has significantly lowered the entry barriers for new enthusiasts. The continuous evolution of these applications reflects the rapid advancement of both mobile technology and our astronomical understanding. Improvements in computing power allow for more detailed simulations, while advances in mobile sensors enhance the accuracy of augmented reality features. Simultaneously, ongoing astronomical discoveries require constant updates to databases and algorithms. Mobile astronomy apps have also democratized access to tools that were previously available only to professional astronomers. Orbit calculators, celestial event predictors, and visibility simulators, which once required expensive specialized software, are now available for free or at very affordable prices. To anyone with a mobile device, the integration of artificial intelligence in astronomy apps represents an emerging frontier. Machine learning algorithms can analyze patterns in observational data, predict changes in comet brightness, and even automatically identify celestial objects. In photos taken by users, this technology promises to make future generations of astronomy apps even more intuitive and powerful as we use these digital tools to track our October comets across the night sky. It is remarkable to reflect on how modern technology has amplified our ability to connect with the cosmos. These digital companions do not replace the direct experience of stargazing, but enrich it by providing context, accuracy, and accessibility that transform every moment of observation into a deeper opportunity for cosmic understanding and wonder. There is something deeply moving about the idea of capturing light that has traveled for millennia through empty space, preserving a unique cosmic moment in an image that will endure long after these ancient visitors have continued their journey toward the remote regions of the solar system. Comet astrophotography represents an extraordinary convergence of art and science, where meditative patience meets technical precision to create visual records of phenomena that transcend ordinary human timescales. Amateur comet photography has undergone a quiet revolution over the past 2 decades, transforming from a highly specialized practice reserved for photographers with expensive equipment and deep technical knowledge into an activity accessible to anyone with a digital camera and the patience to learn fundamental techniques. This democratization of astrophotography has created a global community of celestial image hunters who collectively document the most spectacular cosmic events of our time as we approach the photography of our October 2025 comets. The first fundamental principle to understand is that we are working with extraordinarily small amounts of light spread over relatively large areas of the sky. Comets, although they may appear bright to the naked eye, are low-contrast objects that require specialized techniques to fully reveal their structure and beauty in photographs. The modern digital camera, with its electronic sensor capable of accumulating photons during long exposures, has capabilities that significantly exceed those of the human eye for detecting subtle cometary structures, while our eyes see comets as fuzzy spots with perhaps a hint of a tail. A camera can reveal tail structures extending several degrees across the sky, complex brightness variations in the coma, and sometimes even jets of material emanating from the nucleus in particular directions. Basic camera setups for comet photography require an understanding of the fundamental relationship between sensitivity, aperture, and exposure time. Sensitivity determines how sensitive the camera sensor is to light, but higher sensitivities inevitably introduce digital noise, which can obscure subtle details. Experienced photographers typically seek the highest ISO that produces acceptable noise on their specific cameras, often in the range of 800 to 3200 for modern cameras. Aperture, represented by the F number, controls how much light enters the camera during each exposure for comet photography. Generally, we want the widest aperture available, typically f divided by 2.8 or wider, to maximize light gathering. However, wider lenses can introduce optical aberrations at the edges of the field of view, requiring a careful balance between light gathering and image quality. Exposure time presents perhaps the most interesting challenge in comet photography. Comet exposures that are too short don't capture enough light to reveal subtle cometary structures, but exposures that are too long can result in stars appearing as streaks due to Earth's rotation. The 500 rule, which suggests dividing 500 by the focal length of the lens to determine the maximum exposure time before stars start to show noticeable movement, provides a useful starting point. However, comets add additional complexity to these considerations because they move noticeably against the star background during long exposures. A bright comet can show noticeable movement during an exposure of only 30 seconds, creating an image where the stars appear as points, but the comet appears slightly elongated. This feature can be aesthetically appealing, emphasizing the comet's dynamic movement through space. Tracking mounts have revolutionized amateur astronomical photography by allowing much longer exposures than are possible with stationary cameras. These devices slowly rotate to compensate for Earth's rotation, keeping stars as fixed points during exposures that can extend for several minutes. Mounts like the Skywatcher Star Adventurer, Optron, and Skyguider Pro offer professional tracking capabilities in portable packages accessible to amateur photographers. The stacking technique represents another fundamental advance in modern astrophotography. Instead of relying on a single long exposure, photographers can take multiple shorter exposures and combine them digitally, using specialized software. This process improves the signal-to-noise ratio, revealing more subtle details, while minimizing the effects of digital noise and atmospheric aberrations. Stacking software such as Deep Sky Stacker or PixInsight can automatically align multiple images based on star positions, compensating for small camera movements or mount drift. For comets that move noticeably during a photography session, the software can alternatively align on the comet itself, resulting in a perfectly defined comet against a star background that shows streaks indicating relative movement. Lens selection plays a crucial role in determining which aspects of a comet will be most prominent in the resulting images. Wide-angle lenses from 20 to 35 millimeters can capture extremely extensive comet tails in their full context, but may make the nucleus and coma appear relatively small. Telephoto lenses from 135 to 300 millimeters can reveal detailed structure in the coma and inner tail region, but may not capture the full extent of long tails. Photographic composition in astrophotography requires unique considerations that differ significantly from conventional terrestrial photography. Landscape elements can add dramatic context and scale to comet images, creating compositions that connect the cosmic with the terrestrial. A bright comet photographed over a recognizable mountain or iconic tree can create images that resonate emotionally with audiences who might find purely astronomical photographs less engaging. The digital processing of comet images requires specialized techniques that differ from those used in conventional photo processing. Comets typically exhibit extreme dynamic ranges with bright nuclei surrounded by extensive but faint tails. Careful tone mapping can reveal structure in both regions without saturating the bright nuclei or losing detail in the faint tail regions. Comet-specific enhancement techniques include deconvolution filters or lose details in the faint regions of the tail. Specific enhancement techniques for comets include deconvolution filters that can sharpen blurry details caused by atmospheric turbulence and directional filters that can emphasize linear tail structure. However, these processes must be applied judiciously to avoid creating artifacts that do not reflect the comet's actual structure. Calibration of astronomical images using dark, flat, and bias frames is a fundamental practice to achieve high-quality results. Dark frames, taken with the same exposure settings but with the lens covered, allow for subtracting the sensor's thermal noise. Flat frames, taken from a uniformly illuminated light source, correct variations in sensor response. And lens vignetting. Although these additional steps require time, they dramatically improve the final image quality. Meticulous documentation of settings and conditions is crucial for serious comet photographers. Recording camera settings, atmospheric conditions, and visual observations of the comet can help optimize future techniques and provide valuable context when sharing images with other enthusiasts. These notes can also contribute to the scientific record of cometary behavior, photography, with smartphones, although limited compared to dedicated DSLR cameras, can produce surprisingly good results for bright comets. Modern phones with night photography capabilities can capture prominent comets, especially when used with tripod adapters for stability. Specialized apps can provide manual control over exposure settings not available in standard camera apps. Safety during nighttime astrophotography sessions requires careful consideration, especially when working in remote locations. To escape light pollution, carrying red flashlights, dressing appropriately for night conditions, and informing others about location plans and schedules are important precautions. Astrophotography often requires long sessions in isolated locations, making safety preparation especially important. The cometary astrophotography community is notably generous in sharing knowledge and techniques. Online forums, social media groups, and local astronomy clubs provide valuable resources for photographers in development. Sharing images and seeking constructive feedback can significantly accelerate the learning curve for specialized techniques. Opportunities for citizen science abound in comet photography. Amateur images can contribute to scientific studies of tail development, brightness changes, and fragmentation events. Organizations like the American Astronomical Society maintain databases of comet observations that include contributions from amateur photographers. The time-sensitive aspect of comet photography adds urgency and excitement to the practice. Comets are temporary targets that change night to night, and the best photographic opportunities may last only weeks or even days. This ephemeral nature makes each successful photo session feel like a special achievement, capturing a moment that will not be repeated in the foreseeable future. Ongoing technological evolution in camera sensors, processing software, and tracking mounts means amateur astrophotography capabilities continue to expand. More sensitive sensors allow shorter exposures for the same results, while improved processing algorithms can extract more detail from given data. This evolution keeps the field constantly exciting for experienced practitioners. Comet images also serve important educational purposes, making complex astronomical phenomena accessible to general audiences. A well-executed photograph can communicate the beauty and scale of cosmic events in ways that verbal descriptions cannot match, potentially inspiring interest in astronomy among people who otherwise might not have considered the subject. When we finally capture that perfect image of our October comet visitors, with their tails gracefully extending across the star field, and their coma softly glowing against the cosmic background, we have achieved something remarkable. We have preserved a moment of an event that will not repeat for millennia, creating a tangible record of our participation in the great cosmic dance constantly unfolding above us. Invisible to many, but eternally fascinating to those who see it, who take the time to look up with curiosity and wonder at the great tapestry of cosmic time where events are measured in millennia, and observation opportunities can be separated by periods that exceed the entire duration of human civilizations. October 2025 stands out as a truly exceptional moment. The simultaneous convergence of two bright and observable comets, each following orbits that take them away from our earthly neighborhood, for periods that defy ordinary human understanding, representing an astronomical opportunity that transcends not only our individual lives, but potentially the lives of countless future generations. To fully appreciate the rarity of this moment, we must contemplate the timescales involved in cometary movements. The Swan Comet, with its orbital period of approximately 22,500 years, completed its last approach to our inner solar system, when woolly mammoths still roamed the frozen steppes of Siberia and North America. The oldest known cave paintings were being created by our ancestors in European caves, and organized agriculture had not yet begun to transform human societies from nomadic hunter-gatherers. When Swan returns again after its current pass, humanity will have undergone transformations we can barely imagine. If we maintain the current pace of technological and social change, the civilizations witnessing its next return will be as different from us as we are from those prehistoric artists who left their handprints on cave walls 22,500 years ago. The Lemon Comet, with its slightly shorter but equally extensive orbital period of 1,350 years, connects us with more recognizable but equally distant historical events. Its last approach occurred during the period historians call the High Middle Ages, when Gothic cathedrals were being built for the first time, when Vikings sailed to North America, and when Islamic empires were experiencing their golden age of science and philosophy. The coincidence that these two cosmic travelers with such different orbital periods and probably distinct origins in the remote regions of our solar system converge in our sky during the same month of October represents an extraordinary statistical alignment. Orbital calculations suggest that such coincidences of multiple bright comets are events that may occur once every several centuries or even millennia. To properly contextualize this rarity, we can examine the recorded history of notable comet appearances. Halley's Comet, perhaps the most famous of all comet visitors, due to its relatively short orbital period of 76 years, has been documented in historical records for more than 2 millennia. However, even with its relative frequency, Halley's Comet has been visible only 29 times since the beginning of the Christian era, underscoring how rare even the most predictable comet events are. The great comets of history, those bright enough to be seen with the naked eye and to leave lasting impressions on human societies, appear less frequently. The 20th century, despite its advances in observational astronomy, witnessed only a handful of truly spectacular comets. The Great Comet of 1910, which appeared the same year as Halley's Comet's return, creating a double celestial spectacle not seen in centuries. Comet West in 1976 and Comet Hale-Bopp in 1997. Comet Hale-Bopp, discovered in 1995, perhaps offers the most appropriate comparison to our visitors of October 2025. Its orbital period of approximately 2,500 years, Hale-Bopp was visible to the naked eye for 18 months, a record longevity due both to its considerable size and favorable orbit. Its appearance marked the first time in decades that the general public had the chance to observe a truly spectacular comet without the need for specialized equipment. However, even Hale-Bopp, with all its grandeur, was a solitary event. The simultaneous presence of two bright comets, as we are experiencing in October 2025, is phenomenologically different and statistically much rarer. Historical records suggest that such double events may occur only once every several millennia, making our era truly privileged. In terms of comet observation opportunities, the unpredictable nature of cometary behavior adds another dimension. to the rarity of this moment. Comets, especially those making their first approaches to the inner solar system in millennia, can behave in unexpected ways. They can fragment under the thermal stress of solar heating, experience sudden increases in brightness due to the explosive release of volatile materials, or fade prematurely if their ice reserves are depleted faster than anticipated. The fact that both Swan and Lemon have survived their solar approaches and remain observable during their close passes to Earth represents a fortunate event in itself. Many promising comets have disappointed observers by disintegrating before reaching their full observational potential. Comet Ison in 2013, for example, generated considerable excitement before fragmenting during its close solar pass, providing only disappointing views instead of the anticipated spectacle. The availability of modern technology during this exceptional cometary event adds entirely new dimensions to its historical significance. While observers of past centuries relied entirely on visual observations and rudimentary sketches to document comet appearances, we now have access to digital cameras capable of capturing extraordinary structural details, spectrometers that can analyze the chemical composition of cometary comas, and global communication networks that allow instant sharing of observations and discoveries. This convergence of a rare cosmic event with advanced technological capabilities means that October 2025 will likely be the best documented cometary event in human history. Every aspect of these comets' behavior, from subtle variations in brightness to structural changes in their tails, is being recorded with unprecedented precision by thousands of observers around the world. The scientific implications of studying multiple comets simultaneously are equally extraordinary. Individual comets may show idiosyncratic behaviors reflecting their specific histories and unique compositions, but when multiple comets can be observed under similar conditions during the same period, scientists can begin to distinguish between universal features of cometary behavior and peculiarities specific to individual objects. The simultaneous observation of Swan and Lemon also provides unique opportunities for comparative studies of cometary activity. These comets, likely originating from different regions of the outer solar system, may exhibit subtle differences in composition reflected in their emission spectra, gas release patterns, and tail morphologies. Such comparisons can provide valuable insights into the conditions prevailing in different regions. During the early formation of the solar system, the temporal rarity of this event also gives it special cultural and educational significance for most of the living human population. This will be the only chance in their lifetimes to witness a double cometary spectacle of such magnitude. This reality creates a collective responsibility to fully document not only the scientific aspects of the event, but also its cultural impacts and the human responses it generates. Human societies have historically responded to bright comet appearances with mixtures of awe, fear, and scientific inspiration. Comets have been interpreted as omens, inspired art and literature, and catalyzed advances in astronomical understanding. The October 2025 event, occurring in an era of global, instantaneous communication and widespread scientific literacy, may generate cultural responses of entirely new types and scales. The democratization of access to astronomical information means that people from all cultures and educational backgrounds can participate in this cosmic event in ways that would have been impossible during similar historical events. Mobile applications provide real-time observation guides, and social media platforms enable instant sharing of photos and experiences. And online educational resources make detailed scientific information accessible to anyone curious to learn. This widespread accessibility also means that the October 2025 event can serve as a catalyst to spark interest in astronomy among populations that have traditionally had limited access to direct scientific experiences. Comets, with their immediate visual beauty and accessibility for observation, represent ideal gateways to a deeper appreciation of astronomical science. The educational implications extend beyond individual interest to opportunities for structured educational programs. Schools, universities, museums, and planetariums around the world have organized special programs taking advantage of this unique moment. These programs not only teach about the comets themselves, but also provide broader context about orbital physics, solar system chemistry, and scientific research methods. The temporary nature of the event also creates urgency that can motivate participation that might not occur with more permanent phenomena. The realization that this specific opportunity will not recur within human lifetimes can inspire people to make special efforts to observe, learn, and engage in ways they might not consider for more routine events. The records we create during this exceptional period, whether amateur photographs, detailed scientific observations, or simply personal descriptions of our experiences, will become valuable historical documents for future generations. Just as we value historical records of past comet appearances, future generations will examine our records from October 2025 to understand both the astronomical aspects of the event and the responses of 21st century human society. The prospect that our distant descendants may one day read our descriptions of these comets while preparing for their own encounters with the same objects after they have completed additional orbits, spanning millennia, adds a dimension of intergenerational continuity to our current observations. We are creating temporal links that connect the present with futures so distant they can barely be imagined. The statistical rarity of this event also reminds us of the fundamentally unlikely nature of our conscious existence in a universe where most matter and energy are arranged in forms that cannot contemplate their own existence. The fact that conscious beings arose on this planet precisely at the moment to witness this extraordinary cometary convergence represents a coincidence that is simultaneously humbling and inspiring. As we watch our October comets slowly move across the night sky, carrying ice and dust that formed before our planet existed, we are witnessing a direct connection to the material origins of our solar system. These objects are time capsules, preserving conditions from more than 4.5 billion years ago, and their temporary visit offers us unique opportunities to study these primordial materials. October 2025 will be remembered not only as a moment of exceptional astronomical beauty, but as a convergence of cosmic opportunity, technological capability, and human curiosity that created ideal conditions for exploration, discovery, and wonder. In a universe where such convergences are extraordinarily rare, we have had the privilege to participate in one that may not be repeated for millennia to come, making this moment one that truly transcends the ordinary limitations of human time and connects our brief lives with the eternal rhythms of the cosmos.